My name is Hagai Eisenberg. As I was introduced, I'm a professor of physics at the Hebrew University, and I'm also one of the founders and chief scientists of HEQA security. This will be the only talk, it seems, today that will not be about quantum computing, but about another vertical or pillar of quantum technology that was mentioned here, which is quantum communication. And actually, I'm taking a different approach than others. I'll only present the company at the end. I'll mainly introduce you to the current trends in evolution of this field. And we'll start. So when we are talking about quantum networking or communication, we can see three stages of evolution. First of all, the first application is quantum key distribution. This is the main field that HEQA was focusing on until today. And then you can see the evolution towards next generation, which includes other applications. In a moment, I'll detail a little bit more about this. And then we can see in the future connecting computer and sensing devices in different ranges, either short range or long range. So if we try to follow the evolution and trends in quantum communication, the previously and currently and the main thing is about data security. So this is again quantum key distribution and derivatives. And the applications are various in government, banks, health, cloud, critical infrastructure that needs authentication, access, and what you can see are either terrestrial links or satellite links, and we envision the future with combinations of both terrestrial and satellite. This will be the most common, probably, ways to transfer information, quantum information from place to place. And because we are talking about data security, it's mainly about security, so you can see the keys connecting. But today, there's a lot of evolution towards the next generation of applications, which, first of all, they will require more complicated networks. So what you can see here is like my envisioning of a simple network where now at the end there are some devices. I don't want to call them even computers, but you can. And then we need for these two main components, entanglement source, which is compatible with communication, and what people are talking about calling quantum repeaters. Again, I'm not explaining anything. This is not a technology presentation. And when you'll have that, you'll be able to do more than just data security, like clock synchronization, secure clock synchronization. It's very important for cellular networks, for data centers, for army applications, defense applications. When you're talking about GPSs, these are all clock synchronization devices. And then distributed metrology, like you can think about quantum synthetic aperture, like quantum synthetic aperture sensors or something like that. And then there are all kinds of applications that we are stumbling upon, like voting, agreement, zero knowledge proof. And in the future, where we are aiming, I'm just hiding these two little quantum computers in Australia here. It's really connecting quantum computers. And then, first of all, the first goal is not about range at all. It's just to enhance the power of quantum computers by parallelization. So everybody before me spoke about making their own quantum computer larger and larger and larger. Eventually, they will hit some limit, and they will always stand at the limit. And let's say the limit is whatever, n qubits, m depth of calculation. But if you have two quantum computers connected, then quantum information can be shared, you get parallelism, and actually you double the number of qubits. And for that, you just need a simple sort of, compared to the quantum computer itself, quantum link. So that will create this distributed parallelization. And you can also think about quantum cloud access and homomorphic encryption, where you hide your algorithm and your data. So there are protocols for that already developed called homomorphic quantum encryption. So these are all future uses, so if we put them on a line. And actually, the main takeaway is the next slide. I want to present to you how there are three primitives, basic primitives, and actually in every basic quantum communication talk, I guess for most of you, it's the first quantum communication primitive talk, but in the future, when you encounter them, you'll see this is what people are talking about. There are 3 ways to transfer quantum information for all the applications that I did show in the previous slide. So the basic one, which is the most intuitive, currently used in most cases, and we will use it also in the future, is called prepare and measure. This is the simplest you can think of. Just take a quantum system. If you want to deliver it, it has to be a photon. Encode some quantum information in it, and let it go on a fiber to a satellite, wherever. And then on the other side, you have to absorb the information somehow, so to detect it with a quantum detector, okay? It depends on what degree of freedom did you use of the photons. Photons can be used in time being, polarization, wavelength, spatial shape. There are many, many ways that in my lab at Hebrew University we encode quantum information too. It doesn't matter. Eventually you have to measure. That's prepare and measure, the simplest one. The other one that some of you may be familiar with is distributing entanglement. This looks like you don't distribute information, because what you do is you generate what are called entangled pair of photons. So you generate the photons in pairs, or actually you can also generate them one by one and then do the entanglement. But eventually at the output of this box at the center, you get 2 photons which are entangled. You shouldn't care now what entanglement is about if you don't know, but you know it's a very prime and central feature of quantum technology, and in a way, the only reason quantum computers have some advantage is because of entanglement, so also quantum communication. And then you distribute these 2 photons to 2 different nodes, and you measure them in the nodes. What did you do? You distributed no information, but if one of the nodes does have some quantum information encoded in its system, it can operate a protocol, again, which I'm not going to explain at all, called quantum teleportation. It takes its own quantum bit with the distributed quantum bit with no information, mixes them in, if you want the physicist, but they know it already, it's called a Bell state measurement. You do a Bell projection, and the result is a magic where your information in your own qubit disappears and reappears on the other side. So in a way, you generated a quantum channel without delivering the real information. This is why people were inspired by Star Trek and called it in '97 quantum teleportation. This is the experiment that was cited in the Nobel Prize of Anton Zeilinger 3 or 4 years ago, exactly this word. So this is the second primitive. The third primitive is less known, and the use cases are more limited, but it's interesting. It's an a posteriori, bediavad entanglement, where both sides actually take meaningless photons. So again, these are photons without information, and they send them to a third party in the center, which is here marked by this line, which is actually an optical beam splitter. And you just detect 2 clicks with no information. These detectors, in this case, just tells you that these 2 photons appeared, one of each of the detectors. So again, no information. Another weird protocol, like everything is in quantum in the quantum world. If this photon or the other one was entangled with the information on one of the sides, so that will be a quantum computer. In that, the largest use case of that will be a quantum computer. Then actually, again, this information reappears a posteriori in that photon. So this photon doesn't exist here, but you did something with it before that, and bediavad, it appears a posteriori. That's what you have done. Actually, you used the information that was encoded here. I know it's confusing. These are 3 primitives. If you are familiar with QKD, it has there's a use case for QKD. It's called the measurement device independent, MDI QKD. Not so useful, but there is one company that sells this kind of products. The last minute or half a minute, I'll just tell you about HEQA, our company. Our goal is to take deep tech, which you all know about, and make it the simplest possible, smallest, cost-effective. And we do that by simplicity. I call this KISS QKD. If you Google, if you go to Wikipedia, I like this value in Wikipedia very, very much. KISS is keep it simple, stupid. And it's an engineering idea. How do you take something very complicated And at the end, you don't want a PhD in physics to operate it. It has to be a communication technician. It has to be a very basically educated person that has to do very routine checks, just plug it in and install, press a button, and it should work. And this is exactly our product. It's the smallest in the world. We pack into one boxes 3 components: the Alice, the Bob, the transmitter, the receiver, and the KMS and the key manager service server. It's small, it's cost effective, as I said, and it's actually being sold. It's a real product, unlike quantum computers that is already being sold all around the world. There are tens or maybe even more than 100 installations all around the world, including major companies that you all know, like hyperscalers, which I cannot name them. All our customers. We are in Modi'in. If you want to visit, you are welcome. Thank you very much for your time.